Alright, we're going to be working with the Section 7.2 Concepts worksheet. In Chapter 5, we calculated area under the curve, such as this. And when I say area under the curve, I really mean the area between the curve and the x-axis. So that if that region were above the x-axis, you would calculate and get a positive value. But if you were to calculate a region underneath the x-axis, that value would be negative, so you needed to multiply by -1 to get that to be a positive value. Or in this section, we're going to calculate area between two curves. It's simply going to be the integral from a to b of f of x minus g of x. So basically top minus bottom. Now it doesn't actually matter whether or not the function is above the axis or below the axis. Taking a look at example 1 here, if we're trying to find the area under the curve, this here is just between f of x and the line y equals to 0, so it'll just be integral of f of x dx. Now what happens when the two regions intersect? In this case, they happen to intersect at 0, so we can say that this is going to be the integral from a to 0 of, remember, top minus bottom, so this would be g of x minus f of x dx, and we have to add to that the integral from 0 to 3 of f of x minus g of x. Now let's take a look at this next one. The region is underneath the x-axis. You can think of the x-axis as the line y equals to 0. So when you write out your integral from a to b, it's really 0 minus f of x dx. Or you can simply write negative the integral from a to b of f of x dx. So if we have a function and it changes from a negative function to a positive function, how do we find the area between these curves now? And now the x-intercept here is at c. So here we have to write this out as the integral from a to c. It'll be negative f of x because it's underneath the x-axis. And then from c to b, that'll simply be positive f of x dx. Over here, if we find the area between the two curves, this is going to be the integral from a to b of f of x minus g of x dx. Now I need you guys to take note that it doesn't matter where the x-axis is on here. It's always going to be top minus bottom. Because imagine if this x-axis were up here at the top. Wouldn't the area between the two curves still be the same? Yes, this would be a translation of our graphs, just moving it up or moving it down. So it's always just going to be top minus bottom. Now number 6 over here, they're both negative functions, and that's again still okay. It'll be top minus bottom. So again, f of x minus g of x dx. Now how about this one? We've got two functions, f and g, and sometimes it's positive, sometimes it's negative. They intersect at c. So how do we write out this area? Well, we need to know from a to c which function is on top. So if you look carefully, g of x is on top, f is on the bottom, and then we're going to add to it the area from c to b of f of x minus g of x. Now the last two that we've got here are going sideways, basically. We've got a parabola that opens to the right and a parabola that opens to the left. When you have something like this, you're going to write it out in terms of y, and instead of top minus bottom, it's going to be right minus left. So pay attention, because on the right-hand side the numbers are bigger, and left-hand side the numbers are smaller, so it's right minus left, not left minus right. So in this case, on the right-hand side we have the function g of y. On the left-hand side we have the function f of y, and this is going to be integrated with respect to y, and our bounds are going to go from c to d, smallest to biggest. Now how about over here on this one? It's going to be right minus left, and here you can think of the left-hand function as being the vertical line with the equation x equals to 0. So we can write this integral out as f of y minus 0, or just simply f of y, and it's going to go from negative a to a. Now, if you notice that this is symmetric, you could also just go from 0 to a and double it. Alright, we're now going to take a look at a few examples. So the first one, I want us to find the area enclosed by f of x equals to 2 minus x squared and g of x equals to x. F of x is going to be a parabola that opens down, shifted up by 2, and g of x equals to x is going to be a line, and so they're going to intersect somewhere. You need to pay attention and make sure you know that the area bounded by the two is this section right here. So you kind of want to ignore the x and the y axes. They are not part of your boundaries. Now we need to know where these 2 points of intersection are, so in order to find that, we need to solve when f of x equals to g of x. So in this case, x squared plus x minus 2. So x plus 2 and x minus 1. So this point right here will be 1, 1, which some of you guys may have already known. This point over here will be negative 2. And what is our coordinate point for the other one? Well, it's going to also be negative 2 because g of x equals to x. So what we can do now is to find the area between the curves. Remember, these are like our Riemann sums. We're going to sum up all of these little rectangles. That's why we have our integral from negative 2 to 1 of f of x minus g of x, top minus bottom. So I have negative 2 to 1 of 2 minus x squared minus x dx. So integrating this gives me 2x minus 1/3 x cubed minus 1/2 x squared from negative 2 to 1. So we'll just take our numbers and plug them in. 2 minus 1/3 minus 1/2 minus negative 4 minus, or actually a plus, 8/3 plus 2. And all of this adds up to 9/2. It's a good thing that it's a positive number because the area between two curves should always be positive. Let's take a look at another example. I want us to find the area bounded by y equals to the square root of x minus 2, the x-axis, and the line y equals to x minus 4. So let's make a little sketch. Y equals to the square root of x minus 2 has an x-intercept at 2. So that's going to be a parabola that opens to the right and only the top half of it. We have our x-axis, which is already on here. And then we have the line y equals to x minus 4. So that has a slope of 1 and a y-intercept of 4. So it kind of looks like this. Now, here's where you want to be careful. Make sure you did not draw y equals to the square root of x minus 2 as a parabola that has both the top and the bottom halves, because we don't need that bottom half. And which region are we talking about? Bounded by these three things. So the curve for the parabola, the x-axis, and this line. There is only one region that is bounded by all of that, and that's going to be this little section. Make sure you don't get this region down here. That is not part of it, nor is this part of it over here on the right-hand side. So how can we identify the area here, or how can we calculate the area? Well, there's a couple different ways to do this. If we write this integral out in terms of x, then you need to know that we have to do the top minus bottom, but we cannot go straight from 2 to, we need to find this point right here, and I'll go ahead and let you know what that is. It's 6, 2. We cannot simply find a straight integral to go from 2 to 6. Can you guys see why? Because the top function, yes indeed, is always the square root of x minus 2, but the bottom function changes. Part of the time it's the horizontal line, y equals to 0, and part of the time it's this line y equals to x minus 4. So we won't be able to write this out as one integral. We will have to break it up at 4. So our integral is going to be from 2 to 4 of the square root of x minus 2 dx, and then we would have to add the integral from 4 to 6 of the square root of x minus 2, and then minus the line, minus x minus 4 dx. This is our top function and then our bottom function. Okay, so this is one way to approach this problem, and I trust that you guys can integrate this after having spent so much time on integration in Chapter 6. Now, there is another way for us to do this. There are several other different ways. I know previously I said we couldn't write our integral from 2 to 6 of the square root of x minus 2 dx, but I guess I was kind of leaving out a few things there. If I wrote out this integral, you need to know that what you would have found is this whole region, the area between the curve, the parabola, and the x-axis. So that's a little bit too much. I actually have this extra piece over here that I need to subtract. Well, you can subtract that either geometrically or with calculus. If you do it with calculus, that's going to be the integral from 4 to 6 of x minus 4 dx. Or you could simply calculate the area of that triangle. This is going to be the 0.62, so that is 1/2 base times height for the triangle. Now, any of you guys see any other way that we could find the area bounded by these curves? Okay, well, one thing that we could do here is to treat our area and our regions with respect to y. We could go this way. And if you take a look at these rectangular sections that I draw, they all have the same right-hand function and the same left-hand function. So it can be done with just one integral. The only thing we need to make sure we do is rewrite our equation in terms of y. So I'll just draw it really quick over here. Our line is instead going to be x equals 2, y plus 4, and our parabola instead will be y squared plus 2 equals to x. Okay, so these are functions in terms of y. So then we would need to integrate, and it's going to be right hand minus left hand. So on the right hand side we have the line y plus 4 minus, on the left hand side we have y squared plus 2 dy. Now what are the regions, or what are the boundaries for our regions? The smallest y value will be 0, and the largest y value will be 2. So this one, although you have to do a little bit of work in terms of solving your equations in terms of y, but you end up with a really nice simple integral. You don't have any square roots left, and you only have 1 versus 2 integrals for the other two problems. I'm not going to integrate these. I trust that you guys can do these on your own. We're going to go back to the concepts worksheet and do the last example that's on here. Here's the graph of y squared equals to 4x squared minus x squared. So notice it looks like a little bow tie. And I want to find the area of the shaded region. We kind of need to rewrite this equation because it's got y squared. So if I write y equals to plus or minus the square root of 4x squared minus x to the fourth, the positive half of this would be the top part of our graph where the y values are all positive. So the top half of this bow tie. And then the negative one would be underneath. So how can we write out our integral here? Well, we can use symmetry to make our life a little bit easier here. If you notice, all 4 sections here are the same, so we could just find the integral from 0 to 2 of the top half, so 4x squared minus x to the fourth, and multiply it by 4. And just find one of these and multiply by 4. Now, do you guys remember how to integrate this stuff? Let me just start this off for you a little bit. I could factor out an x squared, so I'll be left with a 4 minus x squared inside. This x squared comes out. My values of x are all positive. So I have this. You should be able to take care of this with just a simple substitution. If you'd like to do a trig sub, you can, but once you work this out, you should get 32 over 3 square units.